Okay, now it's a recording. So Xingjie, can you start?
Okay. Hello everyone. If you have downloaded this file class DelPhi zip, you can zip it into this folder. And now today we are going to talk about one is DelPhi, the other is DelPhiForce. Before talk about the DelPhi and DelPhiForce, I need to introduce another software, which is a PDB to PQR, because only DelPhi and DelPhiForce can recognize the PQR file instead of PDB file. So before we run this program, we need to transfer PDB to PQR file. Let's say this. First, let's talk about DelPhi. In DelPhi, this is the main software, and then we need to a PQR file, and the other is this parameter file. First, I need to teach you how to transfer to PDB to PQR. Let's see how to do it. First, open terminal in this folder, and then we need to transfer the PDB file to PQR file. We need to go to previous folder, and then go to PDB to PQR. And then in the PDB to PQR file, the software is written by Python. And then this is a calculation, is a method, is charm. Except for charm, we still have the amber. To make sure our calculation is correct, we need to use the same method to calculate the electrostatic force, electrostatic. And then you can type this argument, which is chain. It means to keep the chain name into the PQR, keep the chain name in PQR file. And then let's write the PDB name. Did everyone following me? Anyone got lost? Okay. After this, there are no warning here. We can see.
So everyone, please, if you have questions or if you feel difficulties, please let Xingjie know.
This file is generated by this command line, and you can open this one. You can see this is a PQR file. Oh, sorry. You can open this by VIM. Maybe we can try another way to open it. In case you cannot find the VI in your in that template. Here is the PQR file. Here is the PDB file. You can compare them. Because in the PDB file, we don't have the charge. Here in PQR file, we have charge here. That's the reason we need to use PQR file to do the calculation. Okay, after generation of the PQR file, we can start to modify our parameter this txt file. You can see this. This file have very important parameters. First is scale. Because in DelPhi calculation, the calculation is something like one layer by layer. If the scale is bigger, it means calculate the potential is very in details. That's the reason we need to use the scale. But one is good enough, one or two just enough. If you want to do some quick calculation, you can set it to 0.5. And then is profile. Profile set 70 is it should be 70%. It means your proton occupies the whole volume of your box system. It's around 70. It's a ratio. Means your proton occupy the length of the whole box for calculation. And then the third line is in. In means which PTQR file, which proton you are going to calculate. Here we use this PQR file. The name should be correct. And then the format is the extension name, which is PQR. And in DI and EXDI means the proton dielectric and the water electric. Because in our system we use water, so the EXDI should be set at 18, and the proton dielectric should be set at 2. And then the next one is the BRAD. This parameter means let me check. Sorry. This parameter means this means some accessible surface. If you want to know something in details, you can search the manual, DelPhi manual, to find all the parameter meaning. Except for this, there are also something others. And then 1.4 is especially for water. And then the salt, it means the concentration of the sodium chloride in mole ratio, which is 0.15. And next one, the BNT-CON. This one means the 1 or 2 or 3. It means some. It doesn't mean some mathematical meaning. It's one means. Yeah, here you can find the BND COND. What this mean? This 1 means potential 0, 2 means the diploma something, and 3 means forcing. And you can see all the details meaning of it. And then it's a max. This means the maximum error because in the calculation it uses many iterations. When they find the maximum error is smaller than this, it will stop. And also this one is the limit. It means the limit iteration times. This time is set at 8,000 times to do the simulation. 8,000 times to do the iterations. And then out means the output file. Output file is a cube file. I believe everyone already learned how to open cube file in the camera, which is Wenhan already told us. And then the format is a cube. And this file including all the potentials, electronic statics, and also some energies. And the last one parameter is the energy. This one means which energy you are going to calculate. S means the reaction field energy. In other words, it's the solvation energy. And this time but this solvation energy is only including polar solvation energy, not the non-polar solvation energy are not included. And then the C is the Coulombic energy, which is electric interaction between each other. And then the G is a grid energy. Grid energy is sometimes not very important because grid energy only is meaningful when you compare two protein system, they are using the same grid. But so the gradient sometimes we don't test. We don't do the calculation of grid energy. We can just mutate. It will not calculate. But we can test. Sorry, we can test it. This time, and then after modify this parameter file, and we save it and run DelPhi. How to run DelPhi is very easy. Just DelPhi. This is this is DelPhi, and then put the parameter name here, and then click enter, and it start calculation. And then there will show you many iterations, which is just like I said, the maximal error and the iteration maximal times. Yeah. This is a grid energy, which is G in the parameter. And the Coulombic energy, and the reaction field energy, which is S solvation energy. And this potential map in cube format, you start writing the cube file to make the potential in that. Okay, now we can see the cube file. First, we can start open the PDB file. Then open the cube file. It needs some time. Here shows the progress. Oh, sorry. I need to test this again. Oh, this is the first time I met this error. Okay, I will do calculation again, maybe. Here. Just wait a minute. Yeah, it seems that if we recalculate DelPhi, it seems can make some error in the cube file. So you need to delete the cube file first, then run the DelPhi calculation. And then, okay, the Q file already in here. Here, you can see some gray and black layers cover the protein. It means it's a potential layers. And just like Wilhelm told us before, we can choose the surface, show the surface. Yeah, the calculation surface also need time. And the model panel, don't say this. And the action can color it. Sometimes too big, I will use 3 or 1. Color it. Now is how we get the electronic static surface. From the PDB to PQR, then use the PQR file to calculate the cube file. Then upload it and map it by the cube file. So you can get a pretty beautiful figure of it. Okay. Anyone have some question? If you got lost, you can just tell me. I can show you if you have some questions. Okay, no question. I'll move forward to the DelPhiForce. Now I already know how to calculate the PDB to PQR file. And then in the DelPhiForce, here is DelPhiForce. We also need to use the DelPhiForce we also need the PQR file. Let's open the PQR file first. Oh, by the way, the PQR file also can be opened by the camera. Here. DelPhiForce calculates the force between the protein. But the force, when one is reference, the other is your target protein. In this time, we want to say the top one. Here is the myosin. The blue one is the myosin, and the how to say that? The green one, the yellow one. The yellow one is the actin filament. We want to say how the force, the atoms, maybe the residues in the myosin, I mean the blue one, affected by the actin in here, in the yellow one. So we need to prepare two files and separate them, and then transfer this to PQR file, one is actin, one is myosin. Then we run the DelPhiForce. In DelPhiForce, the method how to calculate is not like the DelPhi to calculate the electric static. And maybe we can delete all this file first in case some error. And only the two files is good enough. We don't need to prepare some parameter files. And but we need to use the DelPhi, this folder. This folder including some very important files like this. We need to use the DelPhi C++ and the DelPhiForce sh. And these two will be used in the DelPhi calculation.
Excuse me.
Okay, here.
Go back to DelPhiForce folder.
Yeah, DelPhiForce.
I want to know which one is deleted.
Just keep the PQR file. The others are all not important.
Okay, thank you.
If you don't delete, that's fine. I have tested DelPhiForce can overwrite, but in the DelPhi it seems cannot. There will be some error. Okay, anyone have some problems? Just unmute yourself and tell me. Okay, I will move on. We already prepared the PPR file here. Then we go to the how to set DelPhi. Oh, by the way, because we need to this DelPhi C++, we need to use the absolute pathway. So we need to find the absolute pathway here. This is very important. You can see your folder which one is it. We cannot use the relevant pathway. We need the absolute pathway to calculate the DelPhiForce. Let's go back to the class DelPhiForce and in this folder. And first, we need to get the DelPhi.sh, the shell script file. This time we can use the we first get the DelPhiForce sh, and then first parameter is acting, and then the second one is Melson, and then we use some tools to calculate it. So where's the tools? Just like I showed you the PWD, PWH, the pathway, the absolute pathway. I already remember my absolute pathway, but if you cannot remember, you can go to that folder and tap the PWH to find and copy it. And then is the output file. It's O, not 0. Remember, this is the O. And you can name something like out. And then click enter. It start calculation. It will usually take some time. Usually it will take about 10 to 15 minutes. Depends on your system. During this time, I can maybe solve some questions. Or you guys, if you have some questions, just ask me.
My display, some files were created. Is it right?
Sorry, can you say that again?
My display, some files were created.
Some files created.
Yeah.
Yeah. There will be some file created, some log file, txt file, and some other files.
Okay.
Yeah. Maybe we can skip this process, and I have some already successful result.
Yes, please. If you already have the result, let's do not wait. Let's see the result directly.
Okay.
Thank you.
Okay, this one is 1000 folders, and we can try this one. After generation, you will see all this kind of file. It should be totally same, except for the PDB file. I already deleted this one. And here, it's alt TCL. Remember, the TCL file is how to show that in the VMD. Let's go to the VMD first. First, if we calculate the actin, you need to download the actin PQR file first. This is already present by Wenhan, so I'm not going to say too much since November. Then in VMD there are some TK console. In this terminal, this one is the TK console is based on the TCL script. So the prepared while the TCL script is already prepared well. So first I'm going to change the background to white for better visualization. What happened? Oh, maybe the previous TCL file is broken, so I will change the background by myself. Okay, change it to white. And then run, because we already got the alt TCL and alt residue TCL. These two are going to show you the first alt residue TCL. Sorry. In the TK console, we need to use the source to run some TCL file. It's clear. Yeah. Okay, let's see this arrow, this red arrows here. This means a force. Where is it generated? Since I typed it wrong. Sorry, I should load the mousing first, then load the acting second, but it's not Not much, it doesn't matter. You can see this. This is the out residue T cell. And you can see, can everyone see the red arrows here? It means the residue here are affected by the force generated by the actin filament. All these red arrows. Then if you want to see the total force, and you can source out TCL. This file, including all the this blue one, this navy blue one, means the total force of the myosin affected by the actin filament. Yeah, and if you want to see the result of the force, you can get into the folder which one out atom and out residue. Let's see out residue first. And Fx, Fy, Fz means in the three dimensions of force, and all this one means different residues, residues ID, and then if you want to calculate total force, you just take the square of this and sum together and get a square root. Yeah, that's you can do the calculation in your future work. This is all the result. And the out TC and there should be another things. And yeah, the out atom, out residue means the force of every atom affected by the actin, and then the out TCL. You can see how they draw this one. Yeah. And why at first I show some wrong commander because I didn't use source because this command I typed wrong. Yeah, this is this one, the source home, because I need to run this TCL script first, which is already in in the folder I provided. It's this one, draw arrow TCL. Then you can source out.tcl or out residue TCL to get it. And now we get the force between the two protons, and also know how to calculate the DelPhi force to know the electronic static surface. And if you have other questions, for example, the parameters are not very clear, you can go to the website, the computational this one, DelPhi force software management. It's in Clemson. And go to the DelPhi manual PDF. You can see all these very important parameters or explanation of this one, of the DelPhi. For DelPhi force, you can also search. It's also in the also in the same group. And here are some descriptions, download the link, and also some important manuals in here for you if you want to learn the details, some code, something. Yeah, I think that's all. Anyone have some questions about running it? Hello? Anyone have questions?
No questions.
Okay, thank you everyone.
Thank you, Shunjie.
I will stop sharing.
Okay, thank you.
Thank you, Dr. Lee.
Okay, I'll stop record.